This meeting is being recorded.
Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, March 28, 2025. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a cloudy evening here in my hometown of Rockport, Massachusetts. These Earth and Space reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining biosphere, and who wonder about the greater cosmos and all that it has fostered throughout space and time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on the 1623 Studios Community Access Cable Television channel. I'm grateful for the continuing interest and support shown by Rockport educators and students, Cape Ann cultural colleagues, cohorts of the Gloucester Area Astronomy Club, yay, myriad Earth and space scientists, educators, and communicators, far-flung friends, family, and other curious folk. Thank you for your active participation and encouragements. This evening, we will explore weird moon facts and the importance of being wrong. Our interlocutor is Seth Lockman, a native of Maine who has developed a wide-ranging portfolio of programs in public outreach and STEM education across the state of Maine. Shortly after graduating college, Seth created a weekly half-hour talk show about the night sky and the universe. During its 4-year run, the panel interviewed some amazing guests from all across Maine's quietly thriving aerospace industry, performed for live audiences, and presented at STEM festivals across the state, including 2 night sky festivals in Acadia National Park. Seth spent another 4 years leading the communications team at one of Maine's 2 rocket companies. He has since helped grow the digital footprints of STEM education companies around the world. Recently, he has become a member of the Science and Entertainment Exchange under the National Academy of Sciences, where he serves as a science technical advisor. I came to know Seth in his continuing role as a NASA Solar System ambassador and most recently as an affiliate member of the U.S. National Astronomy Education Coordinator Team, which is hosted by the International Astronomical Union's Office of Astronomy for Education. In his lunar presentation this evening, Seth guarantees riveting delivery, infectious enthusiasm, and scientific accuracy to 4 significant figures. So let's get going. The Zoom platform is all yours, Seth.
Thank you so much, Doc Waller. Thank you for having me here. And if I may do just one little plug for our state, the Artemis 1 aeroshell that was protecting the command module was made in Biddeford, Maine.
Huh?
So it was the first part of the rocket to touch space. All right. So yeah, I've prepared a chat just about some weird moon facts. This is a presentation that I typically do at the middle school or high school level. And it's all about the importance of being wrong. And I want to sort of give some credit to my inspiration in this and a lot of the work I do, which is at one of those Acadia Night Sky Festivals. I was fortunate enough to get to see Wally Funk speak and even speak with her in person after. She was one of the, I think it was the Mercury 13. So these were a number of women who went through the same tests that the Mercury 7 did, the men. And some of them even outperformed the men, but they simply were not permitted to go to space because it was just not something that women really did at the time. Wally did finally get to go. She rode on a Blue Origin capsule a couple years ago now. And but I got to see her before that, and she was just this absolutely amazing person who, the thing that really struck me about her, other than, all of her many accomplishments as an aviator, was how she really approached not knowing something as being like an amazing adventure, not like a shortcoming. If she didn't know something, because I got to hear her talk to a number of people, she never apologized or acted ashamed or anything. She would always just ask questions and be so excited that she was about to learn something. And that was a big part of her the talk she gave too about her life and how she was just like, I'm gonna go here and learn this new thing, right? That like almost like ignorance is opportunity,
Mhm.
and therefore a very temporary state. And so I have tried to embrace that in my own life imperfectly. And this was the first talk that I've ever built around not just being like, hey, kids, here's how the moon is, but really around we're going to come up with an expectation and we'll run through some examples together. And unless there's a couple of smart Alex in the audience tonight, the odds are that we're going to be wrong the moment that our prediction comes up against some measured results from historical missions. So I don't know how we normally do participation wise, but it seems like kind of a small crowd. So folks just want to like unmute and jump in. I am totally fine with that. If for the sake of decorum, maybe we're like chatting and typing in comments in the chat, and then Bill will like moderate. Totally fine with that too. But I'm not like married to the deck or anything. I love going off on tangents. In fact, actually, let's calibrate our interactivity now with a quick little activity. So I'm going to share my screen. Not to brag or anything, but I got really good at this during the pandemic, all these virtual presentations. All right, so is everybody seeing like a blank black screen now? Okay. So the first thing I want to do is it involves the moon, but it's a little exercise in sort of breaking away from functional fixedness, the frame of reference, colloquially, that we each use to view the world. And on this, I think we're all probably pretty well aligned. So if I were to ask you, what time is it in this photo? What would be like, some guesses? I would love to just like have people throwing out some ideas.
Early evening.
Makes sense? Yeah.
Full moon.
For sure. Yep.
Once in a blue moon.
Yep.
Why not dawn?
Could be. It works both ways, right? Yeah. Okay. So clearly full moon, and then we're looking at early evening or like dawn, right? So that the sun is either just gone down or just about to come up, right? And in fact, this is an old astronomy picture of the day, so we happen to know it's a vernal equinox moon, so around this time of year, and it's Madrid is the city, and it's about 8:39 at night when this photo is being taken. Long exposure. What if I were to tell you that somewhere in this photo, it's noon? You're like, oh, good God, I just booked like 45 minutes with a crazy person. Right?
Say that again. What was the question?
If I tell you it is noon in this photo, somewhere in this photo.
On the moon.
Right. Yep, right here along roughly this meridian, right? Anybody standing on that line, at the instant this photo is snapped, they would experience that as noon and be looking up at night on Earth. You guys are fast. So zooming out a little bit, right? This is the Earthrise photo, and I care entirely too much about this. This is the original orientation of the photo. NASA rotated it 90 degrees so that it would like hang on walls better. But those guys weren't in a polar orbit, right? They were in an equatorial orbit. So this is what it would have looked like. I know they were in a barbecue roll, but this is actually within a couple of degrees what it looked like when they snapped the photo. Anyway, once again we have the same thing where these astronauts are roughly above like where noon is, right, down and off to their right, and then they're staring at Earth, and you can see everything from noon to just shy of midnight. over on the far side. Can everyone see my mouse
Yes.
pointing? Okay. Ooh. I have. Now it's an astronomy presentation. Got our laser pointer going. All right. So the point of the exercise is to just ease people into being wrong and stepping outside of the box and realizing that we're actually just in a larger box, right? This is it's hopefully it's like fun to think about, but you know, this isn't exactly like profound stuff. It's just a different way of looking at things. That time, at least the way we measure time, can also be thought of as a measurement of movement through space or location. Okay, so the presentation is called Weird Moon Facts. We're going to start with like some fairly normal moon facts. Moon's diameter is about 2,200 miles. It's a little bit less than the distance from San Francisco to New York. It is surprisingly small by mass. It's only like a little over 1% Earth mass. Its orbital velocity is fairly confident that a blackbird could fly that fast through Earth's atmosphere. Obviously, it's not going to achieve orbit because that close to Earth, you need to be going much faster. But yeah, by the time you get out to like 250,000 miles, you only need to be going 2,300 miles an hour for a stable orbit.
You're referring to the jet, the Blackbird jet, right?
Yes.
Okay.
Yes.
Just checking.
Oh yes, no, not the bird, not the yes.
Hmm.
An African or a European blackbird. No.
Mm-hmm.
Yes. By the way, on a good day, I am a well-read enthusiast, not an expert. So please, by all means, just jump in if I'm forgetting something. Okay, so orbital inclination is about 5 degrees off the solar ecliptic, but off of Earth's ecliptic, it's like it'll swing between 18 to just shy of 30 degrees. The moon doesn't have any moons, though that is theoretically possible. And if you consider things like the Lunar Reconnaissance Orbiter as an artificial sub-satellite, then it does have a couple, but our moon doesn't have any moons. No atmosphere to speak of, although we will come back to that in a couple minutes. No magnetosphere to speak of. There is a surprising amount of ice, and that's something that's changed, relatively recently. Certainly, when I was learning about the moon in school, we were taught what an incredibly dry place there is. There's no water there at all. And then it was, discoveries in the 2010s that really led us to realize there's not just like theoretically maybe a little bit of ice up, in some polar craters, but actually like a pretty fair amount in the regolith at higher latitudes. Of course, the moon is tidally locked to Earth, so 1 Earth month is the same as sort of like a lunar year and a lunar day. So whenever we start having like blue collar jobs on the moon, the morning show will be like a week long. Surface temperature varies pretty wildly from -400 to like 250. And that's, of course, not just day and night. That's the side facing the sun versus the side away from the sun. So that's why the barbecue roll is so important in Apollo. Surface area is slightly less than the continent of Asia here on Earth. Surface gravity, 1/6 of a g. So if you want to punch in some numbers, as I tend to do, we're talking 5.32 meters per second squared. It is an eccentric orbit, but basically 250,000 miles is the average distance. 5th largest moon in the solar system, and it is the largest moon in the solar system relative to its parent body. So every larger moon is orbiting a planet that is much, much larger, like Titan or something. Okay. Hopefully we're not bored to tears yet. I'll take it. Okay, so let's get into the weird stuff. Okay, so let's talk about twilight rays or corpuscular rays or God rays. They're actually unironically called in some circles. So this is like, inspirational posters of like a beautiful sunset with like those rays coming down or up if it's sunrise. They're bright streaks that will sort of occur when there's either just really high contrast between some unobstructed patch of sky and then like something that is obstructed, usually a cloud. But it can be helped to get a really strong sort of like feeling of like almost like that beam is a physical thing. Sometimes if there's an abundance of like dust particles in the way, you'll get something that's, really pronounced and striking. So this is my little diagram of a sunset. I don't have, like rays coming up. This is supposed to be the sun. Outside of Earth's atmosphere, it would appear as sort of a white star. And so at this point, I would sort of open the floor up and say, ignoring this foreshadowing for a moment, keeping in mind that the moon has functionally no atmosphere. It's very, very tenuous, right? What would we expect for a sunrise or sunset to look like on the moon? Would we see, any like rays like that, or like sundogs, or any of those types of formations?
I would imagine no.
One would, right?
I mean, there's nothing to stir it up, no dust, no atmosphere. Only if you had a meteor impact and you had a cloud of crap.
That's good. Yes. So some sort of ejecta, like a momentary thing
Sure.
that would scatter the rays somewhat. Yeah. But outside of like exceptions like that, we wouldn't really expect to be seeing these twilight rays coming off of the sun. Right? We're all, yeah.
No.
Oh, I see. Okay, most both cameras are off. Okay, that's cool. Okay, so here's where things get a little bit crazy, though. So going back to the surveyor missions, so these were probes that were sent ahead of crewed missions to the moon, basically like scoping out landing sites, practicing descent profiles, taking some basic measurements of the lunar environment. And as early as Surveyor 1, the very first mission, touched down successfully, they took this picture here. So it did land right side up, but the camera was upside down for some reason. If someone happens to know why, let me know in the chat. But this was an image of the sunset. And you can see like the disk of the sun, the photosphere is like totally below the horizon in this shot. But there are some structures here, like here in particular, here, maybe here a little bit, where it kind of looks like, maybe they're tenuous, but it looks like there's twilight rays there, right? And a number of folks were like, no, that's the corona. And everybody had to be like, well, yeah, no, that could be. I mean, it kind of looks, certainly the corona would still be visible in the instant that this picture was taken. The sun had just dipped below the horizon, so maybe it was like some aberration in the camera lens or something like that. But this stuck with folks, a couple of them anyhow. Maybe this was like a confirmation bias thing, but obviously the Apollo astronauts were aware of the information coming back from the Surveyor program, and 5, 6, and 7 also got stronger detections, including from orbit of these rays. But there was still skepticism, and the astronauts were coming back with stories of, seeing these twilight rays in just a couple of seconds before the sun peaks over the horizon and the sort of the lunar dawn. And I don't think, no astronauts would have experienced lunar dawn like on the surface. This is all in orbit, right? But finally, Gene Cernan, the commander of 17, he just sketched it out on the flight manual and said, look, this is what we're seeing. This is what, we've been seeing this whole time. And there were still some folks that thought, well, maybe these guys are imagining it. Maybe it's a prank, right? There was like still some skepticism that we were actually seeing twilight rays, because of course the Surveyor missions also very conclusively demonstrated that the moon has functionally no atmosphere, right? There's a little bit of stuff off gassing from the rocks, but it's a vacuum, right? How on earth could there be ray scattering up there? This has to be something else. So also on the moon missions, right, there were these ALSEPs, Apollo Lunar Surface Experiment packages. These guys were essentially technicians, right? They would take the LEM down, gather samples, set up the ALSEP, and then leave. But a fair portion of each mission was setting up sort of a suite of sensors that would just measure different things. And on Apollo 17, so same mission, so Gene was drawing these rays and also helping set up this particular sensor, which was the Lunar Ejecta and Meteorites Experiment, or they called it LEAM. And the purpose of LEAM was to detect ejecta, which I think was something that Arthur mentioned when we were all sort of speculating, right? So a meteorite slams into the moon, it kicks up all of this fine dust. Some of that escapes entirely. Most of it settles back down to the surface, which is how you get this sort of, several feet thick layer of dust covering most parts of the moon. And so they thought it would be really interesting to get like a frequency detector that so LEAM would just be sitting there, and every now and then it would get hit by like a sudden burst of many collisions would be detected, right? It could get a sense of the energies involved in those collisions by the speed of those dust grains. And every time there was a spike in detection, and the number of collisions sort of went up and then went back down, right? Every one of those spikes would be presumably a micrometeorite impact. And so we could get a sense of like, what is the frequency with which the moon is being bombarded? You can take that information and try and sort of generalize it to the rest of the solar system and take a look at cratering across the surfaces of the different planetary bodies and come up with more refined estimates for the ages of all of these planets and moons that don't have an atmosphere. So the near goal is to learn something more about the moon and then hopefully apply that to other celestial bodies. And in fact, when we finally got those really crisp images of Pluto in New Horizons, and realized like, oh, there's not enough craters on that surface. Mm-hmm. A lot of that data started with this LEAM experiment on Apollo 17. So anyway, they set it up, hook it up to the solar panels and everything, and it's just, passively detecting micrometeorite impacts, larger stuff if it's farther away. And it started detecting something kind of weird, which was that every dawn there would be a huge spike, and this is in hours from sunrise as our x-axis here. So if you were detecting ejecta hitting this sensor from an impact, you would expect that to be maybe a couple of seconds, right? But we're looking at this cloud is lasting for days, actually at this point, almost 3 days after the sunrise, maybe 2 days before, and it's it's this really long curve. I say curve in the sense that it's not a straight line, right? And it was happening every morning. So this is there's no, even if there was an impact on the moon near the LEAM sensor every lunar morning once a month like clockwork, right? This is not the kind of distribution you would get. And then it would happen again in the evening. Not as much. And there's some theories there, which is that on average, the velocity of these impacts that were being detected in the evening were lower. So it's possible that there may have been just as many events in the evening. However, they were not tripping the sensor because they weren't quite energetic enough. Because we're talking like a mean of like 1 meter per second. So that's like, pretty slow for grains of dust. So that's weird. Something's like causing dust to rise up into the air and then fall back down rather gently every lunar morning. Another piece of the puzzle came from the LADEE mission. So this was much later in 2013. And this was the mission that actually did confirm that the moon has a very tenuous atmosphere. It's 1/10 trillionth of an atmospheric pressure. It's mostly argon and a little bit of helium. And they also found out that the moon actually has two tails, kind of like a comet, one of gas, one of dust. The one of gas is mostly sodium. So that's cool. It also was the first mission to use lasers to communicate. So everything up until now was basically broadcasting. But LADEE was testing out, they called it the Lunar Laser Communication Demonstration. So this is like, I don't know if anybody is reading The Expanse, but this is like your tight beam, right? This is the birth of this technology, or at least the birth of its use in space. So it had a laser link to 3 different ground stations, and it would communicate that way instead of broadcasting by radio. Also, it had an incredibly low orbit. So at its lowest point, perihelion was like 10,000 feet. For comparison, the surface ceiling of like a Cessna Skyhawk, the most common like little propeller aircraft, single engine, you've probably seen tons of them, right? So its surface ceiling these days is about 13,000 feet. So this thing was flying or orbiting lower than the Cessna can fly on a good day. And of course, the lower your orbit is, the faster it's going to be. So this thing would go screaming over the mountaintops at about 3,700 miles an hour. So it's like almost 1,500 miles an hour faster than the lunar modules or the command, the Apollo missions were orbiting the moon. So technologically, it was a fascinating mission. And part of what they were trying to do by flying so low was to fly through these clouds that seem to be getting kicked up every morning and see what kind of detections that could be made, similar to missions that fly through comet tails. Also, this is maybe not such a technological achievement, but this is possibly like the most interesting photobomb in NASA history. So everyone see the frog there? All the other frogs are jealous of that leap. I'll tell you what. The condition of the frog is uncertain. But there was a little bit of like a sensation. Everyone was like, "Oh my God, the frog!" This is the launch of LADEE. So LADEE's up there in the fairing, getting ready to head off to the moon, orbit low, and make these detections, see if it can figure out what's going on with these dust plumes. And LADEE also had one of the first like high res cameras, like megapixel cameras, to leave Earth orbit. Excuse me. So this is time lapse of LADEE, screaming by like 3,200 miles an hour, skimming the lunar surface, and there we see the sunrise. And I don't have the ability to pause this. You can see that the camera is getting saturated, but clearly in those latter frames, we're not just looking at corona, right? That is too irregular. So this is considered the first conclusive proof in late 2013 that indeed there is ray scattering going on in the lunar sunrise and also the lunar sunset, and it is the result of dust being thrown up. But obviously it's not just ejecta, right? The LEAM experiment is implying that this is like a very gentle process. So what gives, right? And so the last piece of the puzzle came from sort of maglev trains. So there's a team of scientists that they took some imitation lunar regolith, and they just started bombarding it with radiation and electrons, trying to imitate what the sun, what sunlight and solar wind would be doing to the surface of the moon. And what they found out was that they were able to sort of ionize the outer layer of dust grains. Lunar dust is incredibly fine because there's really no weathering. So you get these very, very tiny grains, which don't take a lot of force to start moving. So what they were able to do is produce these conditions where there's sort of this like flux that's being induced by this rapid sort of like ionization and then reabsorption of those same electrons, and it'll give the outer part of each grain of dust the same electric charge, and like charges repel. And so pretty soon all of this dust, particularly the dust that is just starting to get this solar radiation energy, it starts to repel itself from all of the other dust around it, and all of those dust grains on the surface start repelling each other. They start to lift up, literally to magnetically levitate, and that frees up the next layer of dust underneath to start to get getting energized, have the electrons get stripped away, then the electrons join back together with the atoms on the outside of the dust grain. You have that same charge building up, and so you get layer upon layer of dust rising straight up into the air, because there's really no other weather to speak of, and because the moon is rotating so slowly, the dust pretty much rises like straight up and falls straight down. So like Neil's footprint will still be there for hundreds of millions of years or whatever. So the degradation of those sort of artifacts like footprints on the moon maybe gets sped up very, very slightly by this new discovery, right? Those projections just got a tad shorter, but not much.
What's in the blue box in the UV panel?
That's a really good question. I honestly don't know. I'm hoping that's a grain floating right there. I can click through to the primary source and get that for you, but maybe we'll circle back during question time.
Frog's egg.
I've got a question.
Yeah.
This is really going to sound bizarre. This is an ultra high vacuum around the moon. It's in the minus 13 range. When the sunlight is coming onto the surface, and they're telling about a gas, they're detecting gases, molecules of gas. Dust doesn't do molecules, it's dust. And it's charged, but it's dust. I'm wondering if the gas that they're detecting is basically the sun warming the ground and it's outgassing. I worked in high vacuum for my life. So outgassing of the moon molecules of gas that actually becomes a partial atmosphere somewhere, maybe bringing it into the minus 11 or 10 range, which would be pretty dirty in ultra high vacuum. So that's my question. You think it's outgassing from the temperature difference between minus 200 or minus 400 to plus 200, outgassing the moon's regolith, not the dust. The dust may contribute, but I'm talking about molecules of argon or water, oxygen, whatever the sun is breaking the heated regolith up into with its own rays. And that's my question, I guess.
That is an awesome question. I will do my best to make as educated a guess as I can. Okay, so yes, the moon does have a very tenuous atmosphere, and yes, it is almost entirely generated by outgassing, by sublimation, and it is it's mostly argon-40, helium, sodium, and potassium, all stuff that you would pretty much just excite right off of a rock, and it would form that very thin gas layer, and then pretty much immediately be blown off into deep space. The measurement I have for atmospheric density is 1/10 trillionth what we have at sea level here on Earth. So whether that would be enough to contribute to this ray scattering, I would have to defer to an expert, but those are the numbers that I have to work with from like NASA press briefs and peer review papers and stuff like that. So my understanding is that the ray scattering is primarily coming from the dust that's being sort of like electrically levitated off the surface. But yeah, could the gas be contributing? It depends on whether that 1/10 trillionth of an atmosphere, whether ray scattering in such a tenuous atmosphere would be detectable by the human eye or any of the cameras that we've used.
How high does the dust actually get into the area?
Oh gosh. I want to say it's like 30 meters, but that's just going off of memory. I don't have that right in front of me. But not super high. All right. Well, thank you. Was that Tom?
Thanks, that's all right.
Thank you, Tom. All right. This is another fun one. The lunar far side highlands problem. Okay, so this is another moment where I sit down to kids and I say, hey, we've only seen one side of the moon, basically. It librates a little bit, right? But basically, that's what we know the moon looks like, right? And it wasn't until the 60s that we finally started to see what the back of the moon looked like. But, obviously we had reason to assume it was a sphere. It was a fairly regular, object in space. So if you could make a prediction, what would you say the back of the moon looks like, right? We've seen half of it. How about the other half? So if it's all right, I'll open up to the floor and we'll brainstorm on that again. Say again?
Totally different.
Somebody read ahead. Yep. So usually when working with the kids, right, they say, well, we'd expect there to be, more of these craters, more of these, what are these? Oh, they're lava lakes. Isn't that cool? There's like these frozen lava lakes. Sometimes, someone will ask, well, hang on, if those used to be lava and then they cooled down, they froze, it's just like rock, right? They probably contracted, right? So is the whole moon, did it shrink as it was cooling down? The answer is yes. But basically, maybe a couple of ejecta blankets, a couple of these lava lakes. What you see here is pretty much what you'd expect to see on the other side. So in 1959, this is the Luna 3. This is a Soviet mission, and they took some images from the far side of the moon. It was one of the first space probes to not have all the film come back to Earth on like a tiny little capsule with a heat shield. So it had to actually beam back the images by radio, and then it burned up when it returned to Earth's upper atmosphere. So this is one of the first ever radio transmitted images taken from space, and this is the first image of the far side of the moon ever taken. Obviously, the resolution is not great. This is no LADEE mission here, but we do notice there are some spots here that look like those mare. Not nearly as many, not nearly as large, right? So that's really weird. Strong indicator that there are very different forces at play for the near side versus the far side of the moon. Why would the side closer to Earth have lava lakes, and only that side? And in fact, future missions would confirm that the typical lunar crust thickness is 30 kilometers on the near side, and it gets up to 100 kilometers on the far side. So the crust is thicker. Your average elevations are way higher, and there's also slightly more cratering on the far side, but you wouldn't be able to tell that from this. So why did this happen? Well, of course, we all know about the giant impact hypothesis, right? This is what started it all. Two planetesimals collided, fortunately, with sort of an edge-on thing. So most of the debris was able to recoalesce. More recent models are suggesting that the moon formed very quickly. Initially, it was thought to be like a years-long process. Now we're thinking inside of a month, perhaps even a week or two, the moon sort of coalesced out of all of the ejecta that was still glowing and therefore sticky, and made it into orbit around what was now Earth. Then, of course, everything had to cool down. And that was a hundreds of millions of years process. So this is simulation based on LRO data of what that would look like, specifically the moon cooling. Question? Okay. So as these asteroids are hitting the crust of the moon, which at this point is very thin, it's almost like popping a water balloon. And so the crust, which was already contracting, starts to collapse over under its own weight. And the lava that is still inside, because most of the moon is still just a blob of lava at this point, and just comes right to the surface. Now, this is where things get really interesting, because we think about tidal forces, the moon acting on the Earth all the time, right? Who here sails? I do. Tide charts, right? We're always thinking about them. But when the moon is mostly a blob of lava, there's lava tides. And at this point, the moon was also, pulling a lava tide on the Earth. But because of the inverse square law, the gravity on the near side of the moon will be slightly stronger than the gravity on the far side of the moon. So because of those tidal forces, there's going to be slightly more leakage of any of those little, perforations in the crust, in the super thin crust. There's going to be more gravity pulling that lava towards the Earth on the near side of the moon, right? And then on the far side of the moon, the lava will still leak out, but the tidal forces are actually pulling it towards the Earth, which means like towards through the inside of the moon, almost. So there's not going to be as much leakage on the far side of the moon. Yeah, Mario.
So I understand what you're saying, but back then, the moon must have been rotating. So it froze in place over a number of billions of years, not right away. So if it's rotating relative to the Earth, then there wouldn't be a preferential side. So I'm not sure what you're saying there.
Yes. So I don't know what models you're thinking about, but my understanding is that the tidal locking happened pretty early after the giant impact. That particularly when you're dealing with fluids that are able to slosh around, that tidal locking will occur faster than if you just have solid objects that can't really react or redistribute their mass in response to gravitational meeting. But yeah, had the moon still been spinning when all of this happened, then the whole model would fall apart. Anyway, there was another period of bombardment, and more ejecta started to cover that, that one particularly large lava lake in the center of the near side. And there we have our modern moon. All right. Third weird moon fact, moonquakes. So going back to the Apollo missions, right? Each mission had one of those all SEPs, lunar surface experiment package. And for 12, 14, 15, and 16, they included something called the Lunar Passive Seismic Experiment. Basically, the goal was to measure subsurface properties, particularly small vibrations from moonquakes. And by small vibrations, I mean that nearby the sensors, they sort of dug a hole, tossed a couple of grenades in, and detonated them to sort of see what would happen and calibrate the sensors. Not happy to stop there, they also took the ascent stage of the lunar module, and on 5 missions, they would just crash that back into the lunar surface, about, within 50, 60 kilometers of the seismometer that was part of each of these sensor packages. So each ascent stage is like 2.7 tons, and some back of the napkin math puts the impact speed at somewhere between 1,800 and 2,500 miles an hour. Not satisfied to stop there, they also started smashing S4Bs into the moon. So that top stage they use for the translunar burn, they would just crash those into the moon, also sort of near these sensors, because they could calculate what kind of disturbance they would expect, assuming, if you crash one of those into the Earth, negating air resistance, what would that look like? And they could compare those predictions to the data they were actually able to get from the seismograph. So once again, I would ask folks, what would a moonquake seismogram look like? And some folks may already know. But I set up some axes for you here. So, at least in my mind, right, if you're dealing with a sort of a seismic event that's the result of something crashing like that, it'd be pretty quick, right? You go like, you'd have some displacement on, this could be on X, Y, or Z axis, but it'd be pretty sudden, pretty sharp, and then maybe like a couple more reverberations, and then inside of 5 seconds, probably inside of 3 seconds, you're sort of like back to normal, right? Certainly, at this point here on Earth, we've got like YouTubers that are like dropping cars from helicopters. I don't know if anyone ever saw that whistling diesel video. And then there's some folks in, I think it's Australia, that like just toss stuff off of this like really high tower. So we've actually, dropped, nearly that much weight here on Earth. So we know exactly what that's like now. And it turns out what we actually measured was nothing like what you would expect if you were to just drop a heavy object on the ground. Because what they measured, and this is the Apollo 12 ascent module that they smashed back into the moon right near that first ALSEP. And the moonquake went on for like hour and a half, basically. You can see the initial impact event here, and then it actually gets bigger. It amplifies before it eventually dies down. Now, between you and me, that looks more like what happens if you were to put an accelerometer on like a guitar string or something, right? Than what you would expect from just a seismometer on the surface of a planet. So this raised some eyebrows. And Werner von Braun, actually in an op-ed, he described the moon as ringing like a bell, which is probably where we get a lot of the hollow moon conspiracy theory stuff, which I am absolutely not here to promote, but certainly this is, very remarkable. As to the explanation that we were able to eventually land on, basically the result of having all of these seismometers stationed all across the near side of the moon and measuring not just ascent stage impacts and S4B impacts, but also quakes that are the result of the crust settling as the moon continues to shrink, and also just asteroid impacts, even higher energy events than what we were able to generate so far. This kept happening, and the most likely explanation, well, there's actually a couple of things. First off, moon doesn't have any oceans. Here on Earth, the oceans actually absorb a whole bunch of the energy of the plates shifting around, or the land, getting all wobbly as the result of an impact. Of course, then you have tidal waves to worry about, but that energy does have somewhere to go. Also, our best models put the moon's crust as being way thicker than Earth's crust. So proportionally, right, Earth's crust is like between 5 and 30 kilometers thick. So it's like 0.8% of the vertical distance going down the radius, right? For the moon, if we consider the part of the mantle that is basically inert, right, like frozen solid insofar as rock is frozen, it's solid 63% of the way down. So if the moon is hollow, it's not a very good use of real estate, honestly. But it's a very, very thick eggshell. It's basically a single tectonic plate with a couple of cracks due to compression breaks, and more than half of the moon's depth is just part of this single solid structure. And then it's suspected that even farther down there is some molten, inner mantle and core still. But basically, the energy from these impacts, it has no way to dissipate other than heat, and there's no rocks to rub together. It's all just one rock for the most part. Mm-hmm. So that's how you get the moon ringing like a bell in these cases. The biggest earthquake on the moon was like a magnitude 5.5, I think, is what's been detected. Problem is, they can take a whole afternoon, and so this will be a challenge when building on the moon, figuring out how to adapt for that. We don't need to withstand an 8, but we do need to withstand a 5 for like 2 hours, and then it's a 4 for another hour, etc. And that's the story of how we figured out that the moon's crust is way thicker than we thought. Okay, I do see we're coming up on 8 p.m., so I do have one more weird moon fact I'd be more than happy to nerd out about, but if we need to wrap things up, I will understand that as well.
Well, let's give it a try.
All right. Well, let's talk a little bit about rust. Hopefully this is what everybody gets to see tomorrow morning. Obviously, this is not a picture of the moon rusting. This is a lunar eclipse.
That was the one that we were supposed to see a few nights ago.
Yeah.
The lunar eclipse.
Oh, sorry. Tomorrow morning is not a lunar eclipse?
No, solar.
I even knew that. Yep. My bad. Sorry about that. Yes. Right. Yes. Okay. So yes, I did miss this then. But yeah, Earth comes between sun and moon, casts this sort of ruddy shadow. So anyway, if you ever wanted to know what your reflection looks like from a great distance, it's that. Okay. So I guess we'll talk real quick about like what rust is. Basically, you have some iron, you have some oxygen, and you produce hematite. So Fe2O3. That's like the simplest version of rust. There are other types. For example, Mars is famously rusted, right? But that's a different compound. It is the same basic process. What I didn't bother putting in this simplified equation here is that if there is water present, it will act as sort of like an electrolyte, and it'll speed up the reaction, and it'll also sort of embed itself into the hematite, sort of like how there's carbon in steel. It'll just be water suspended throughout the hematite, and that's how you get, depending on the abundance of water within a hematite rock, that's how you get all those different colors and consistencies. Same thing goes on with ferrohydrite. It's just a slightly different reaction, but that's why Mars rocks look a little bit different than like this type of rust that I'm talking about now. Okay, so we all know where this is going, right? But if we were to have to make a prediction of how much rust is on the moon, what would we all say? Like none, right? Because there's certainly no liquid water on the moon. Basically no oxygen, right? Argon was like the biggest thing in the atmosphere. So there can't be any rust on the moon, right?
You'd think.
Furthermore, in a redox reaction, the iron has to be giving up an electron. And in a situation where the moon is constantly being bombarded by free electrons as part of the solar wind, if an iron atom were to give up an electron, it would just get another electron back from the solar wind long before it stumbled upon some oxygen atom to bond with. So it's not like impossible, but it must be super, super rare if it happens, right? Wrong. So there was a NASA-built sensor on the Chandrayaan mission, and this was back in 2020, so I believe it's still in orbit now. And basically, the Moon Mineralogy Mapper sensor picked up strong indicators of hematite, yes, at the poles where there is water ice, where we could have some ejecta being kicked up by micrometeorites. Some of that water ice could then, it would sort of fly away from the impact site, sublimating and outgassing the whole while. But it would, some oxygen from that water would eventually touch down on other parts of the moon and be freed up through photochemistry. The hydrogen would just get scared off, and there'd be an opportunity, a very brief moment where that oxygen could combine with iron in the moon rocks. So there was clearly some of that going on, especially concentrated in the sort of the higher latitudes, the polar regions. However, Chandrayaan was making these detections of hematite all over the moon, right near the equator. So yeah, all throughout the latitudes. One thing that was kind of interesting is if we think 180 degrees is sort of like the far side of the moon, right? So looking at these charts up here, we do see that there is clearly more hematite on like the near side of the moon. So that's a clue. Fun fact, there is hematite on Mars as well, but that's not the reddish soil. That's like the blueberries that you may have heard about in Mars rover reports. Okay, so hematite on the moon. So iron is somehow resting on the moon, and it's on the side closer to Earth. Another fun fact, another piece of the puzzle, right? Earth is losing weight. We take on about 40,000 metric tons of micrometeorites every year, but we outgas about 50,000 metric tons of just atmosphere every year into the solar wind. The vast majority of that is lighter stuff, hydrogen, helium, but there is some oxygen in there as well. And also, fun fact is humans, when we lose weight, most of that is through exhalation. So we're not so different from Earth in that sense. While Earth is losing mass, kind of like early on, we were talking about stars losing mass. It was like some tiny, tiny proportion of the sun is just getting shot off into space every year, right? Similarly, we're losing something like 100 quadrillionth of our mass every year. So it's not bad. And certainly, even though we're losing oxygen into space, like there's planets and diatoms making more of it. So not to alarm anybody, but once that oxygen does eventually sort of, some of it percolates up to the top of the atmosphere, gets scared off by the solar wind. Well, it's not uncommon for an electron to get stripped away. So suddenly that oxygen has a +1 charge, right? Well, all of a sudden, it sort of starts spiraling around out into the magnetic tail of our magnetosphere, which is not a sphere. And it starts following these field lines. And at certain times in the moon's orbit, so when it's, basically, opposite, so it's a full moon, it's like opposite from the sun, right? And then maybe like the 2 or 3 days on either side of that, the moon is both protected from the solar wind by Earth's magnetotail, meaning that the surface is no longer getting bombarded by free electrons. What it is now getting bombarded by are these trace amounts of +1 oxygen that just got, sort of riled up out of Earth's upper atmosphere. And it's hitting that iron on the lunar surface. And that iron is now eager and able to give up its electron and perform that redox reaction. And so you get this nice sheen of hematite, this oxidation on the outside of all of these iron moon rocks.
Doesn't take nitrogen.
Say again?
It doesn't take nitrogen.
I'm sure that there is also nitrogen that it's arriving on the moon this way, but being real fuzzy on my chemistry, I couldn't tell you exactly why, but it's not bonding with the iron in the way that the oxygen is. I think nitrogen just generally is not very reactive, right?
True.
Yeah, diatomic nitrogen is not very reactive at all. Single nitrogen, I think, can react.
Yeah. But yeah, that's what I've got. Those are my weird moon facts.
All
Moon's
right.
got dust storms every morning and evening, lava lakes, but only mostly on one side. Moonquakes that last for hours, rust, and all kinds of stuff that we didn't get to this evening.
Thank you.
My pleasure.
What a weird place.
Yes. So thank you for letting this government licensed nerd yap at you for an hour. And if you have any questions, I'm more than happy to take them.
Well, I have a question. I'll start things off.
Fire away.
You're relatively young. You could probably go to the moon and spend time on one of the lunar bases.
I would love to.
Would you like to do that?
Absolutely. Something that I asked. So I teach math, and so at the start of every semester, you're getting to meet all the students, and you're supposed to ask, what's your favorite color, or like, what's a movie that made you cry, something like that, right? So the question I always ask is, if you could, assuming sort of near future technology, 100% chance of a safe mission and safe return and all of that, how far out would you go? Would you go to low Earth orbit, the moon, Mars, or beyond? And just about everybody says the moon is like the sweet spot where you get to experience weightlessness, you get to experience being on another world, but you're not really committed to going anywhere for more than like a week.
Mm-hmm.
Mars is like a big time commitment. They're concerned. And I used to be like, yeah, send me to Neptune, man. But yeah, now I'm in that moon camp myself pretty squarely.
Yeah. So much closer.
Yeah. If they had a 2-week package, though, I'd take that.
Any other questions?
Nope, not right this minute.
Fair enough. Well, if questions do come up, my email address is right there. And if I don't have the answer, I can certainly, it would be my pleasure to dig through the primary sources. Only thing I'd add to that response is when I do eventually go to the moon, of course, if possible, I'd love to book passage on one of those inflatable ships, like Bigelow's working on. So they're working on like cloth modules so that you can essentially fold them up to get way more surface area into a fairing, and then you sort of inflate on orbit, as opposed to having like a rigid body, metal module. So you can get just a lot more volume for the same mass that way. And I am curious as all get out to see if it would be just a little bit like a bouncy house.
I've seen them perform burst tests on the material.
Yes.
Bounty house sounds very cool.
Being on the inside, maybe a little bit weird with 0G.
Yep. Yep. There's just a little give there. I mean, what a way to spend 3 days on the way to the moon, right?
The
Yeah,
Velcro
bouncy house.
yourself around.
Sounds wonderful.
All right. Well, unless there's any more fervent questions, I think I'll call it an evening and thank our locutor. I didn't say that right. Seth.
Not our tormentor.
I'll take it.
And I wish you great futures with your aerospace and STEM ventures. And as a solar system ambassador, it's a great thing that you're able to be a part of.
Well, thank you so much. And I feel
And
very
keep
fortunate.
teaching. Keep
Oh,
teaching.
yes.
Oh yeah, keep teaching. It's how you learn.
Getting to be mud season.
Sorry?
Getting to be mud season up in Maine.
Oh, yes. Up here, even our rockets have four-wheel drive.
Excellent.
So
Okay.
thank you so much for this. It was fun. I enjoyed myself.
All right.
Thank you so much.
Take care, everybody.
Nighty-night.
Good luck with
Good
the
night.
eclipse.